All right, so last lecture, we looked at the very fundamental syntax of the language system that we're considering within this lecture series, which was the notion of a first order signature, also known as a first order language. I will just remark briefly that we haven't made any definitions whatsoever so far on the deduction rules for this logical system. So we know how to form sentences, but we don't know how to construct proofs yet. That's not going to be the content of this talk. That's going to be the content of the next talk. But before we get there, I'm going to talk about the semantics of the language that we've just considered. So this is meant to kind of give you the formalism behind interpreting the language that we have just constructed, right? So if you remember last lecture, I was saying a lot that we are strictly only looking at syntax at the moment. When you see a cross, that does not mean that we're looking at a Cartesian product or a categorical product or anything like that. That's up until this lecture. Now what we're going to do is look at that structure inside the syntax and give it meaning inside some kind of mathematical model. And that's the idea of a model. Again, the lecture is going to be similar in that I believe there are issues and philosophical points of, opportunities for discussion, to put it politely, with these definitions that we present today. I'm planning to discuss some of these towards the end. Okay, but let's open with a definition. So inside a semantics is two components. There's going to be an interpretation of a first order language, and then associated to that is going to be, or alongside that is going to be a valuation. And then those two things together are going to be used to define our semantics. Okay, an interpretation. Asset theory here. Let me just make that language. Consists of the following data. Oh, sorry, I forgot to mention. So I'm only saying, I'm only saying one non-empty subset here. Sorry, one non-empty set here, because for simplicity, I built this lecture around considering the special case where our first order language only consists of a single source. So let me make a note about that. Okay, so for the entire lecture today, we're going to assume that the first order languages that we consider consist of a single source. Okay, and so we have a non-empty set D called the domain. We also have, for every function symbol, an associated function. Which maps from the n-fold Cartesian product of D into D. In the special case where the function symbol is of zero arity, then the interpretation of F is simply a choice of element inside D. Okay, so maybe I didn't spell this out explicitly in the last lecture, but inside a function symbol is associated to each function symbol is its type. The arity of the function symbol is the integer given by one less than the length of the type, because b is included in the type. And that's called the arity, and so you might say a function symbol is it's an n-ary function symbol, and so if it's a zero-ary function symbol, then that's sometimes referred to as a constant. So what I'm saying here in other language is the interpretation of a constant is just an element of the domain. Okay, and then we also have an interpretation for all of our relation symbols. And this is also interpreted as a function. But here we map from the n-fold Cartesian product of D into the 2-point set. Okay, so that's the definition of an interpretation. Now what we want to do is extend this definition to the rest of the components associated to a first order language. So if you remember in the last lecture, we spoke about the associated terms and the associated formulas. So that's what we want to extend the definition of an interpretation to now. Only holding an interpretation is insufficient in order to do that. And that's because we haven't said anything about the interpretation of variables yet. So we need to come up with a notion of valuation, which is a choice for elements inside the domain corresponding to an interpretation for each of the variables. So let's do that in another definition. So this is just a function. That's the end of that definition. That's nice and simple.
You might want to remove the subscript.
Sure.
That was an artifact of trying to
yeah.
more than one sort.
Mm-hmm. Okay, fair enough. Okay, and so now given an interpretation and a valuation, how do we interpret the terms? And then the next question will be how to interpret the formulas. So I'll move to the next board for that. Okay. Oh, I've written that badly. I'll say, and I just want to name the domain of I, so denotes the domain. Of I by D. Say new is a valuation. I can't remember the language I used. In D. Okay, so we start with an interpretation of sigma and evaluation over that sigma inside the domain of the interpretation. Then we can extend the interpretation to terms in the following way. Okay, so the interpretation of any of the terms which are just variables is just equal to the the valuation applied to the variable x. Okay, and then for terms that are constructed using function symbols, it's a natural recursive definition. So keep in mind I of f is now a function, right? And then I can give that function all of the different terms which themselves have been interpreted. Cool.
Could you maybe give an example
So
of like of interpreting a particular term?
sure. So if I had a okay, let's say that I had a function symbol f from a to a, and an interpretation I with domain the integers, then what I could do is I could say, well, what can I say? How do I define the valuation? So I'm going to say, let's consider a valuation.
Okay, you don't have to fully define the valuation. It's like the valuation
Well,
will just be whatever integer it wants, right?
yeah, I mean, if I want to give a proper example, I need to show how to define a valuation, which I think is kind of the hard part, right? I mean, if I were to skirt over that, then I could say, I could let the interpretation under V of f to be the function from the integers to the integers that just, I don't know, doubles f.
There's no valuation in this. You're just because you're interpreting what the function symbol is on the domain.
There's no, but did you want an actual example of something fully interpreted? So I thought that you would want the interpretation of f applied to something.
Oh yeah, I'm just saying that if you're in interpreting the function symbols, there's no valuation present there. Do you understand what I mean?
Not for the function symbols. Yeah, not for the function symbols, but for the terms.
Yeah, for the term, yeah. Right. But yeah.
Oh, so you just wanted an interpretation of an example of an interpretation.
No, I was just saying because you wrote subscript new there when saying interpret f as this function, but there's no new to involve there. There's no valuation to involve when you're saying this is in this interpretation.
Oh, you mean here? Yeah, I accidentally put. I succeeded in not putting it there. That was just an accident.
Yeah.
I was meant to not put it there. So this is an example of an interpretation of a function, and indeed, I don't need a valuation in order to describe this. But if I were to give an interpretation of a term of which f is not an example because I haven't applied it to any variables yet, then this is insufficient. I do need to give a definition of a valuation. Do you agree?
Yeah, I sort of, I think it is still like a non, it's not part of the practice of doing logic to like really fully define evaluation. And I think the sort of, the way that evaluation is defined is, oh, you need this like function from that takes any variable and gives like an object in the domain, is like strictly not how it's sort of like used. Like really, we only ever care about like particular variables at one time. And so like sometimes when we speak about valuations, the argument will just go like take any valuation which sends x to this to like 5 and z to 7 or something, and then is just sort of unspecified otherwise. This is done like a bit more like explicitly with things like finite contexts, in which like you actually only specify certain variables. But because like we're supposed to be interpreting everything in the language, that sort of obligates us to like, I guess, fully define evaluation. But I think even in like if you just write v of x, or sorry, nu of x, that's sort of like that's some element of z, and you can sort of just leave that unspecified in this example. I think like that's not
so
really
that makes sense, and yeah, that's how it would be performed in practice. But if somebody asked for an example of evaluation, that would be a legitimately difficult question, right? That's what I thought that you wanted me to do. Like, how do I map from V to Z? How do I describe that?
Request was more like interpreting something like f of g of x and or f of g and x and a or something, like just some complex term. How does the sort of, how do I unwrap that, and how does that become an object of the domain?
Well, I don't really know how to do that.
We don't have to dwell on the example.
Yeah.
But
okay.
just interpret the term f of x just to show what it.
But that's what I'm saying. I don't know how to interpret that. So if I have the interpretation of f of x, is equal to the interpretation of f applied to the interpretation under nu of x, which is equal to the interpretation of f applied to nu of x, right?
Yeah.
But I don't know how to take the next step. I don't know how to describe.
Going this far was my main goal here, and just sort of showing how this definition works. Because like, so you start with, all right, let me interpret this complex term, and eventually you get to, all right, I understand I of f is a function, and I can apply it to some argument. That argument has to be an integer, and yeah, I have an integer because v of x is some integer, and I'm applying a function from integers to integers to it. Yeah. So exactly like this. I think. I hope that's illuminating.
Yeah, that's fine. Oh no! Oh, I'm so sorry. I've got some bad news. My iPad just died. Ah, that sucks. And it's currently plugged into power as well. So that must mean that it was actually losing battery while it's plugged in. Oh, what a pain. Are you able to write up the interpretation of relations? That's literally all that I need to do.
I could write and you could speak.
Yeah, that would be great. Would you mind? Okay, thanks. All right, let's move to the next board.
Dan, are you still there?
Yeah, I'm still here.
Sorry.
One suggestion for future Will is you might turn down the graphics quality settings on your iPad. The battery,
That's a good idea.
yeah, the battery usage is pretty ridiculous with Roblox on the iPad, but you can tweak down the graphics settings, and that doesn't really change at all what you see on the canvas, and you don't care about the 3D stuff, so that should help.
Yeah. Oh, I see. Yeah, I thought it was a problem with my iPad. I did notice massive battery issues every time I use it, but basically every time I use it is with Roblox, so I guess that makes sense. I thought it wouldn't die whilst plugged in though, but I guess I was wrong. Okay, let's get.
Sorry, just give me a moment.
Yeah, no worries. And you have the document, right?
Yeah. I'm just logging in on my iPad.
Mm-hmm.
While he's doing that, yeah, I think your comment earlier today, Will, about we shouldn't take for granted and we shouldn't think that presenting this way is easy, and this is one of the aspects that makes it not easy. And there's not a lot we can do about some of these. Definitely the battery cost of presenting on an iPad here is way higher than on Zoom, right? So there are aspects of this that are clearly like kludges. We can't do a lot about that potentially, but we can at least, have clear guidelines somewhere prominent for how to give a talk and the things to watch out for. So that should be something we'll do.
Yeah, definitely worth mentioning the battery. It sucks that it can die whilst plugged in.
Okay,
Oh
so
well, it's one of those.
definition 3.0.3.
Yeah, but I've already done the terms. So underneath that, you'll see then the interpretation is extended to the formulas.
Yeah.
And you just need to write up all of those. If you could. Okay, great. Thanks. So now the point is to extend the interpretation along with evaluation out to the formulas. And so these are going to be understood as functions, but they map into the 2-point set, which I'm denoting as the set containing 0 and 1, just for the sake of intuition towards these formulas. It's helpful to think of 1 as standing for truth and 0 as standing for false. And this is where the intuition that you had toward the language is going to actually sit. So earlier when we thought of, well, for example, Bill is about to write the second one, which will be the interpretation of equality. So I made the point that that was just empty, naked syntax back when we wrote it down in the context of a formula of a first order language. But now when we interpret it, then the interpretation of that formula is going to evaluate to 1 if and only if the interpretation of the two terms that constitute the equality term are indeed equal elements inside the set that we're currently interpreting it inside. So Bill is literally writing this down right now. Okay, and so that's the way in which we have this very distinct split between the two things that we have presented so far, those being syntax and then semantics. So when we're writing down the syntax, we're writing down term operation rules and similarly formula operation rules. And now we're trying to give meaning to those by understanding them under a given evaluation. So Bill is currently writing down another good opportunity for an example. So this is, I tried to be careful. I can't quite remember if I succeeded in this, but when I was discussing last lecture, I tried to say that we have these rules for conjunction, disjunction, implication, and negation, and I quite pointedly didn't use the words and or. Unfortunately, implies is a close enough word to implication for that to become confusing, but I wasn't thinking about it in that way because they were just syntactical constructions. So given phi and psi, then the formula is we can construct the formula phi conjunction psi, and then only once we consider an interpretation do we put the meaning onto that symbol of and. And that's what's formalized here. Similarly for disjunction and or, similarly for implication and implies, and similarly for negation and not. Okay, the rules for interpreting existential and universal quantification require a bit of a comment. So there is a bit of extra notation which is about to be used. What we want to be able to do is take the valuation that we have and amalgamate it. We're going to change what one of the variables maps to and then consider the resulting valuation. So what we're going to do here is we're going to say the interpretation of there exists X such that phi, that is going to evaluate to 1 if and only if there is a particular element inside D where once I amalgamate new to rather mapping X to whatever it used to map it to. So rather than mapping X to new of X, we now map it to D instead. And then we check whether that evaluates to 1. And if it does, then that's what it means for the existential, the formula has been constructed using an existential construction, evaluates to 1.
I'm just writing a definition there.
Oh yeah, nice. Thanks.
I guess I would say given a valuation V and a variable X and a domain element D, then
the
definition of another valuation, as you were saying.
Okay, cool. And just in case this does confuse anyone, it's worth making explicit that I think Billy and I have both referred to the valuation as new and as V. That's a mistake of the. But yeah, if that is confusing anyone, there's not a new and a V in this picture. There's only one thing, and they're either all V's or all news. You can decide. But I think
I'm not very familiar with new. I did my best to draw it, but
that's all right. I make the exact same mistake. Okay, so the interpretation for all X phi, this evaluates to 1 if and only if for all of the elements inside the domain, once we amalgamate the valuation accordingly and evaluate phi, we get 1. Okay, great.
Should we do an example formula?
Well, I had an example of the first order theory of groups, which gives an example of a first order language and also a first order theory, and then also an interpretation that involves both terms and formulas, but I don't have any relations inside that theory. But I think this still suffices as an example. Okay, Well, let's move over to the first board again and then continue that.
Wait, who's the speaker? Oh, it is. It's just delayed. So what do you want me to write now?
Okay. Yeah, the problem is this is split a little bit. So example 2.0.5 above is where I define the first order language of groups, and then example 3.0.4 is the semantics, an example of a semantics for that.
So do you want me to write down the language first?
Language. Yeah, I think so. Okay, so now let's look at everything that we've done in the context of a concrete example. So what we're doing here is we're giving from top to tail a very strict formalization of how a mathematician might discuss the theory of groups. Okay, so first we need to define a first order language, namely the first order language of groups. Okay, sigma, the collection of sorts, is going to consist of...
Wait, you said in the notes the first order language of groups L, and then you said sigma consists of the single sort.
Oh, yeah, so I did. Okay, that's not very elegant.
Which one do you want me to use?
I kind of want to use neither of them. Just use sigma, I think. Get rid of the L. What did I do down here? I've got a third notation for it later, which I also disagree with. Okay, we'll catch that and fix that up. Okay, so first order theory of groups, sigma. Sigma the sorts of sigma consists of just a single element, G. There are 3 function symbols. Okay, the first is asterisk, which for intuition's sakes can be thought of as motivated by the product operator of a group. And then we also have the inverse. So we wish to build a theory such that every group element admits an inverse. So I'm using an infix notation for this. So what this hyphen to the power of -1 means is that a variable would be replaced for that hyphen. And that means that function symbol applied to that variable. I could have written that differently, but I think this is actually easier once you start using variables. Okay, and then for this theory, there are no relation symbols.
I'm just writing X inverse.
Yeah. Yeah. No, that's good, actually. Okay, and so in this first order theory, first order language, there is an example of a constant. So E is thought of as a zero airy function symbol, which is just thought of as a constant. Okay, no relation symbols. Now, the first order theory of groups, you remember, right, did I actually define that?
Yeah, I don't think we define what a theory is.
Oh, okay. Well, a theory is simple. A theory is simply just a finite collection of formulas. Oh, actually, do we need finite? We don't need finite, do we?
I mean, theories are sort of defined different ways. Sometimes as like usually you would want them to be like defined by some axioms, and whether or not you identify the theory with just the collection of axioms or the collection of axioms with all of their consequences, you can sort of go either way with that. But
no, I don't want it to be finite, because I want to Oh, I guess it doesn't really matter. But I want to be able to consider the first order theory of pure arithmetic.
Yeah, so it can be a recursive set of axioms, so a decidable set of axioms.
Yeah, I see. But you're not willing for just a set of axioms.
You're not what?
Are you saying that we ought not define a first order theory as just a set of formulas?
Oh, actually, yeah. I mean, I think it's fine to I don't know. I think people go different ways on this, but like
In fact,
to be uncontroversial, you can just say set of formulas when you mean set of formulas, and maybe I don't know. You could say a first order theory is just a set of formulas. I'm not really sure.
Let's just go with that. Let's just go with that. Okay. So we're going to define a first order theory over a first order language to just be a set of formulas from that language. And the way that you think about that is it's just the axioms that define the theory, right? So inside this example, we're going to write down the familiar looking axioms from group theory. So the first one is going to represent, and indeed later on be interpreted as, associativity. And then inverses as well as unit. You don't need the for alls, do you? I don't think that you need them, because I'm going to say that a model is an interpretation that holds true under all evaluations. Under all valuations, right? And so when I consider all valuations, I'm going to automatically, that's going to be the same interpretation as this. Like the for alls is just redundant.
Yeah, okay. I sort of remember because like having open formulas, I think was sort of more well suited to the sequent calculus proof system. Usually you just work with closed formulas in natural deduction, but it's not that you can't work with open formulas, but yeah, okay. Well, I'll just write it down.
But it doesn't matter because the interpretation is the same. So if you write down here these axioms without quantifiers, or you write them with quantifiers, the same interpretations make this true, make both of them true, and both of them false. It's equivalent from the perspective of semantics.
Yeah, I think the sort of subtlety there is whether you're using true as like what do you mean by true? Because so to say something is true either involves picking an interpretation or it doesn't. So
yeah, it's true. I mean by true, it is true under an interpretation. So the set of interpretations for which all of these axioms are true under that interpretation, that's the same set whether we consider these axioms or whether we consider them with the universal quantifications, which is my mild argument towards these being equivalent. But anyway, let's just go with this for now.
Do you really not need the inverse on the other side as well? Like x inverse x equals e?
Oh, that's a good question. Yeah, maybe you do. Let's put that up there. Yeah. Yeah, I caught
maybe that's
E, but I didn't catch the inverse.
I'll throw it in as well.
Yeah. Yeah, that's good. Okay, and then to finish off this example, we can look at a model of this theory, which we're going to have the domain of this interpretation as the integers, and we'll see that in fact we'll end up with a group. So let's move over to this next board.
So this continues in 3.0.4.
Yep. So you can see it says let T be the first order theory of groups. Just ignore that, right? So you can just write down equations 27, 28, and 29.
Okay, yeah, I'll just skip to that part.
Yeah.
I'll start over to the left side.
Yeah, so here n and n are just thought of as integers that like they are integers. We are using them in order to define the interpretation of asterisks. So the interpretation of asterisks is the function that will take two integers and then add them together. We also need to interpret the inverse function symbol, and we take that to be the function that maps an integer n to negative n. Good. And then lastly, we need to interpret the zero area function symbol, which is just denoted by e. And remember that for constants, the interpretation is just an element inside the set, and we're going to take this to be the integer 0. Good. And so now let's take an example of one of these axioms that we wrote down earlier. Let's take associativity and think about what the interpretation of that formula would be. Okay, so keep in mind that that entire thing is one formula, right? It's the equality formula constructor applied to the two formulas x times y times z with brackets around the x and the y, and x times brackets around the y and the z. Okay, so this is a formula, and the formulas get interpreted as functions into the 0-point set. So we're going to say that this maps into either 0 or 1, depending on the valuation of the variables. And we say that this is equal to 1 if and only if the interpretation... Oh, you're going to draw the whole thing out? Yeah. Yeah.
So these are two objects in Z, so they're two numbers.
Mm-hmm. Yeah. And we ask for these two numbers to be equal under all possible valuations of x, y, and z. I want you to say here that the original thing evaluates to 1 if and only if it's the case that for all integers n, m, and r,
yeah.
And then write down the equation 32. great. So now we can see how the interpretation of our language actually gave us what we were hoping to get at right at the very start when we wrote down the axiom corresponding to associativity. Okay, and then a similar thing holds for all of the other axioms. You just go through them and you find a model which makes all of them true under all possible valuations. And indeed, what we end up with is every model of the first order theory of groups is just a group. And so therefore we've achieved our goal of coming up with a formal system within which we can discuss group theory. Okay, so that's the end of the lecture. That's the end of the definitions and examples that I wished to give. For whatever time we feel interested to, we can discuss some of the points of hesitation or some of the confusing aspects of it. I guess I'll go first. I kind of dislike this entire thing. To take a language and then map it onto something else which you claim exists. I feel like you're kind of left with the exact same problem. I mean, like, how do we know that this other thing exists? Like, what is the set of integers? What is, like, I feel like this lecture feels very much like I came up with a roundabout, complicated way of writing down this final sentence that for all integers n, m, r, we have associativity. Sorry, associativity. It just feels like, well, if that was already there, available for us to map to it, then what on earth was the point? Like, what did we actually achieve?
I think, like, I sort of feel the same way, and maybe I'll try and play devil's advocate with this. It's kind of like a matter of like compiling, like to when you if you write the language Haskell and you're trying to compile it into a lower language, you replace your Haskell syntax for plus with like a lower level language syntax for plus. And so you don't like answer the question of what plus is, you just sort of like hand it down to like a lower level compiler. And I think the sort of the reason why there's such self similarity here in like having a like our star symbol and then the plus symbol. I think that's just it's the expressibility of like first order logic that it sort of by design reflects the actual language that we like, the only language we have to then sort of analyze first order logic itself. So it's like self-similar by the like, because it's like the tool to use, or the tool that we currently use to analyze first order logic and first order languages is using a very similar language to it itself. In another way, I sort of like you were saying, you like it doesn't reveal anything, and I definitely agree with that, and that's why I've sort of found more meaning in the sort of proof system side of things, because it sort of I don't know, there feels like there's not as much like complete circularity there.
There's not as much complete circularity.
I
love it. Yeah, I agree with you. I think that there's a massive problem with this whole thing. I kind of prefer it when you look at it in terms of topos theory. So to pick the topos of sets in order to interpret first order languages and first order theories in feels a bit evil, because you run into this subtle version of like, I need to believe two things. I need to first believe that I can construct languages, and then I also need to believe in the topos of sets, and then I can interpret my language
topos of small sets.
Yeah, topos of small sets. That does make it a bit better, though, to be honest.
Like, well, that's not a a mild interjection, right? Because depending how you set up your foundations, to even start talking about logic in the topos of sets, you have to choose a large cardinal.
Yeah.
I guess my take on your question is that I think much of the discussion of interpretation and models, I mean, it has its place, but to put it so early strikes me as it has the flavor of a religious belief, right? It's this idea that there's a membrane, and on the inside of the membrane is safe syntax, and I can live in there and nothing bad will happen to me. And then outside the membrane is scary stuff, and who knows what's going on out there. But it's okay, because the logic is just syntax, and it's all good. Now, if you understand the proof of Gödel's theorem, as we will, you can't believe syntax is safe. Like, meta-mathematics is not safe, right? There's nowhere that's safe. But like the language of even the word interpretation has this kind of arm's length feel to it, right? Like, over there is the scary stuff, but like before you interpret, it's just syntax. I mean, this phrase "just syntax" is like oozes confusion out of its pores, right? Like, there's no such thing as just syntax. I mean, you could say there is, but what that's missing is that the rules for writing out and recognizing what syntactic structures are valid syntax and how to combine them is as complicated as arithmetic itself, right?
That's a really interesting take. Yeah, I think that I agree with that. I think that I like the discussion that you and I had about syntax developing into form. I feel like as you discuss simple, basic relations, like going back to the universe that we live in, you understand basic, simple relations early on in life, and then you build more complex relations upon them to the point where you kind of make this mistake where you think that you've identified some semantical object or something inside the physical world that you're living in, when really all it is a pile of syntax that had been delivered to you previously inside your life that you became comfortable with, until like it becomes this point where the syntax does generate the form of objects that we later define further relationships upon. So I agree that there's more to syntax than it's just safe and easy. And I don't know, interpreting syntax inside some abstract mathematical framework which you just presume exists, I think that's just fulfilling your own wish that that's the way that the universe works. I don't think that we've come closer to an understanding of the universe by learning what a model or first order language is.
Yeah, having said that, as Billy has queried me on these topics earlier, it's easy to make snide comments from the sidelines, right? As I just did. It's not like I actually have an answer, right? Like, okay, it's like, fine, all right. There's no syntax isn't safe. Well, fine, but what do you how do you sleep at night then? And then I just say, well, I don't sleep at night, I guess.
Yeah, I think as the target of that comment before, I think like I don't really disagree with anything you said. I've just always been more like, yeah, I can admit that I'm more like comfortable with the syntactic stuff, and I guess I'm sort of like I'm less hopeful now, but I was hopeful of like gaining some like comparable grounding in the stuff in mathematics beyond syntax, and I don't think I've ever been really satisfied by much more yet. I guess that's the sort of goal of this foundations seminar, is like trying to pick apart some of this stuff. But I think one sort of implicit assumption that I'd like to point out is like with the purpose of foundations, I think the way, Will, you were talking before was like your dissatisfaction was sort of around the failure of these definitions to make something. Like, I guess maybe some things in mathematics, like a lot of things in mathematics feel real when like they describe something and you sort of, it conjures images in your mind and you feel that like something has been discovered. And I guess like it's a discovery, but like if you, it sort of feels like sometimes if you formalize it well enough that you've like made it, you've actually created it. And I think like trying to achieve this with like foundational definitions of like the theory and models of everything like is always doomed to fail. And the only thing that's actually left is a sort of like the aim is to still describe or still like discover true things about what's there, like and this is true whether or not there is like circularity in the definition, like whether or not first order logic with ZFC actually makes sets, like actually creates them somehow out of the definitions you write down, like whether or not like that's sort of weakened by this idea of circularity. But the idea that you're still sort of saying true things about these sets that like might still be there even though we haven't made them, like ZFC and first order logic still can say true things whether or not they've actually constructed them somehow.
Yeah, that seems to me a bit like a bit like self-comfort. I mean, if ZFC is inconsistent, it's not like it's a little bit inconsistent over there somewhere, right? It's like the problems will be global and immediate. It's I don't.
Oh yeah. I'm just saying. I'm just sort of like the best we can hope for is to like say correct things about ZFC, and we may or may not do that. And like I'm just sort of saying we can't hope to like create it. I don't think. In the same, like we can't create it in the same manner that I think with ZFC and first order logic as a foundation, we can sort of successfully create the real numbers via definitions. Once you have those tools, the tools of ZFC, you can then make stuff on top of that. But I don't see how you can make ZFC to the same satisfaction without having something already as powerful as ZFC.
I would say the position you just outlined is maybe the standard unconscious mathematical, the position of a mathematician, right? Which is that all of this is aimed at aiding us in making true statements about independently existing Platonic objects. I mean, maybe you don't want to say that Platonic objects independently exist, but if the formalism of ZFC isn't talking about something like real numbers, and if you admit that it can't internally kind of justify a belief in the existence of those things, then somehow you're either just playing a shell game or you admit that those things are out there and you want tools to talk about them correctly. I think I can't reject that idea.
Well, you can only hope that you're talking about them correctly.
Yeah, indeed. Mm-hmm. But, I mean, I think this is to come back to my favorite essay of Gödel's on the mathematics. Is it a syntax of language? It's not that we're playing this game without any feedback from the universe, right? I mean, mathematics appears in all, well, not all, but many disciplines of science and in physics, and the real world does seem to not only in cheap ways, but in impressive ways, whatever that means, to be described by mathematics. And that gives us, what Gödel says in that essay is something like, well, suppose there's a slightly tweaked foundation of mathematics according to which suddenly Feynman's path integrals make sense and you can do quantum field theory rigorously, and then it predicts all sorts of things and you go and discover them. And then people are like, okay, well, we're going to go off and use this new foundation now because it's really useful. What are you going to say to that? Are you going to say like, well, no, those aren't real sets. Those are like, those are fancy new sets. I'm not having any of that. Maybe you'd say that, but like in your heart of hearts, you'd be like, well, maybe those are the real sets, right? Like, nature thinks those are better, and like you can't deny there would be a voice inside you that would be saying that, right? And anyway.
Yeah, that's really interesting. I want a copy of that essay. I don't think I've read it.
I must have sent you like that essay 3 times now. Anyway, I'll send it
Yeah,
a 4th time. Everybody should read that essay. That has bothered me for many years. And it should bother all of you too out there. Okay, maybe that's a good place to... Well, I don't want to leave the final comment for myself, but we should wrap up soon. So are there other observations we want to make?
Will do.
No, that's it for me. No, I'm done.
Okay.
I'm satisfied. All right, thanks. And thanks for redoing the recording, Dan. Appreciate it.
Yeah, thanks very much, Will.